Okay, chemistry class, let's talk a little bit about chapters 19 and 20. I'm hoping that this video will serve as a nice review, looking at everything that you need to know for the test for chapters 19 and 20. Everything from assigning oxidation numbers, redox reactions to galvanic cells, calculating the voltage, the E cell, line notation, all of it. Okay, I'm going to wrap it all up in one video for you, and you can go through it slowly. You can refer back to it. You can use it as a study tool, and I hope it'll be of a great benefit to you. Okay. In chapter 19, we spent most of our time looking at redox reactions. So if you remember, a redox reaction is kind of a two-step process. Something in the reaction is going to be oxidized, meaning it's going to lose electrons, and something else in the reaction is going to be reduced, meaning it's going to gain electrons. So you have to be able to identify oxidation and reduction. So let's look at, in particular, things that you have to do from chapter 19. You have to be able to assign oxidation numbers, because that's really the only way that we can determine if it is truly a redox reaction. You have to see a change in oxidation numbers. Once one particular element's oxidation number has to go up, that's oxidation. The other, a different element or another atom has to be reduced, meaning the oxidation number goes down. It's going to gain electrons. You have to know that oxidation is losing electrons. Oxidation is losing electrons. Reduction is gaining electrons. Reduction is gaining. So together we have a redox reaction. You have to know that an oxidizing agent is something that forces something else to be oxidized. An oxidizing agent is reduced. A reducing agent is something that helps something else be reduced. A reducing agent is oxidized. We have to be able to balance redox reactions, and we're going to do it in acidic or a basic solution, and I'm going to show you how to do that right now. So this example, I hope, is going to incorporate everything here that we just mentioned, the items 1 through 4 that you are responsible for. So let's first assign oxidation numbers. I will give you the rules for assigning oxidation numbers. I will give it to you. In fact, I'm going to show you right now. You're going to get this formula sheet. This is the back side of the formula sheet. You'll notice that right here you've got the rules for assigning oxidation numbers. So that's what you need to know. It's the same one that is on your interactive reader. So let's assign oxidation numbers. Any oxygen in a compound is going to be -2. The only exception for that is H2O2 when oxygen is in -1. It's stated in the rules. And so here's oxygen in a compound, here's oxygen in a compound, here's oxygen in a compound over here. So if oxygen's in this compound and all the oxidation numbers have to add up to the charge, which is a -1 here, then this is going to be a total of -4, plus the Mn have to give me -1, so this has got to be a +3. And here, the O, there are 2 of them, so that's a total of -4, plus the S have to give me a total of charge of 0. So it's going to be +4 here. The Mn is a monatomic ion. It's the same oxidation number as the charge that is displayed there, so it's a +2. And here, H is going to be a +1. So that means the 4 O's, which give me a total of -8, and the H here, which is a +1. So -8 and 1, -7, plus something, plus the S have to give me -1. So that must be a +6. Okay? All right, so we've assigned oxidation numbers. Now we want to identify oxidation and reduction. Oxidation means the oxidation number is going up because it is losing negative electrons. So it looks like the the S is going from +4 up to +6. So that must mean that it is losing electrons because its oxidation number is going to be more positive. Mn is going from 3 down to 2. So it is gaining more negative electrons. As a result, its oxidation number is reduced. So let's split this into our 2 half reactions, oxidation and reduction. Oxidation, again, is the number that's going up. So that is the sulfur. So anything that involves sulfur, these two species right here, I'm going to bring over to my oxidation half reaction. This is half of the total redox reaction. And the two species that are involved in reduction, because the oxidation number is going down, anything that has the Mn in it, I'm going to bring over here to the reduction side. Okay? Now we're going to balance each one separately. It's just easier to do it separately. Balance all the elements, leaving oxygen and then hydrogen till last, and then balance the charges. And the last thing we do is conserve the electrons, and then we can combine them together. So let's balance the S's on both sides. Looks like we already have 1 on both sides. That's good. Let's balance the oxygens. I've got 2 on the left, 4 on the right. I'm going to have to add 2 waters on the left side. Now I've got a total of 4 oxygens on both sides. But now I have to balance the H's, and I do that by adding an H plus on whichever side. So I have a total of 4 H's here, only 1 on this side. I'm going to have to add 3 H pluses on that side. Let's go ahead and balance the charge while we're over here on the oxidation side. Over on the left side, it's a total charge of 0. There are no charges over here on the left side. On the right side, it's a negative and 3 positives. So that's a total of positive 2. I'm going to have to bring that down by adding 2 electrons on the right side. Over here, let's balance the MNs. Oh, it's already balanced. We got 1 on both sides. We balance the oxygens by adding water. So 2 waters give me 2 oxygens on both sides now. Now I have to balance the H pluses. Looks like I'm going to need 4 of them. Okay, so 4 H pluses. And then I'm going to balance charge. On the left side, I have a total of -1 and 4 pluses, so that's a total of +3. Over on the right side, I have a total of +2, because that water is neutral. So I'm going to have to add 1 electron over here to bring the +3 to match the +2 on the other side. Okay, now I have to conserve electrons, meaning the total number of electrons that's lost has to match the total number of electrons gained. It has to be the same number. So I have to multiply one or both of the equations by something in order to get that. So I'm going to multiply everything in this second equation over here times 2, so that I have 2 electrons that are going to be gained. Once I do that, I don't need electrons in my final equation. By conserving electrons, I am guaranteeing that the charges are going to be balanced, and I'll have the correct coefficients when I bring them together. Now all I do is I'm going to bring these together, and all of the reactants are going to be on one side. Don't forget to multiply by the 2 here, times 2, times 2, okay? And then all the products are going to be on the other side. Now, one thing I can also do before I combine these is I can look to reduce some stuff. So, for example, I've got 2 waters here as a product, and I got 2 waters here as a reactant. Those 2 waters are actually going to cancel. So that's kind of nice. And then I've got 3 H pluses as a product here, but over here I'm going to have 8. I'm going to have 8 H pluses as a reactant. So 3 of these are going to cancel 3 of those 8. So these 3 are going to be gone, and this number here then is going to be actually, I'm going to multiply this 2 through so that I can just see it here. Okay, 2. This is going to be 8. Remember, this canceled. This is a 2. Oh, I have to go back and fix this, because this actually I would have multiplied there by 2 by waters. That would have been 4 waters, and now so 2 of these waters will cancel 2 of these. So this is going to become 2 here. So I am going to have 2 waters. And then the 3 H's are going to cancel 3 of these, so I'm going to have 5 H pluses. So looks like a mess, but let's see if we can figure it out here. All of the reactants, SO2, those waters are gone, plus 2MnO4, 2 negative, plus 5 H pluses. Looks like those are all of the reactants. I got my SO2, I got my 2MnO, and then O2 negatives, I got the 5 H pluses, okay? Let's do all the products. HSO4 negative, got that guy, nothing else here, plus 2MN2 plus plus. Remember, those are 2 waters there that I almost forgot about. All right, that looks like that is the final redox reaction. Now, this was assuming it is an acidic solution, okay? And remember, if it's an acidic solution, that's why we were able to add the waters and the H pluses to balance the oxygen and hydrogens. What if it says it's in basic solution? If it says it's in basic solution, you do everything exactly the same. You assume it's in acidic solution, and then you fix it at the end. So all the steps are exactly the same. Now all you do at the end is you say, oh, you know what? This really is not in acidic solution. It's in basic solution. So I'm going to neutralize all of these H pluses. I neutralize them by adding the same number of hydroxides. And if I just brought in 5 hydroxides on this side, I have to add 5 hydroxides on the other side. And now these 5 H pluses and the 5 hydroxides are going to make 5 waters. Okay? Those 5 waters and these 2 waters, you'll notice, oh, they're going to reduce. So these 2 waters are going to cancel 2 of these, leaving with 3. So this would be your final equation if it was basic, if it was in a basic solution. Okay? Everything here that's circled is going to be part of your final redox reaction if it's in basic solution. So that's just a simple little thing at the end that you need to be aware of in case it says basic solution. By the way, that one problem showed you everything you need to know for assigning oxidation numbers, oxidation reduction, balancing the redox reaction. Everything from chapter 19 is in that balancing the redox reaction problem. Okay? All right, let's go to galvanic cells. And let's talk about a galvanic cell. This is all chapter 20. So in a galvanic cell, you have to be able to do all of these things. You need to be able to draw a picture of a galvanic cell, describe and write the half reactions, identify which is the anode and which is the cathode, tell me what direction the electrons are flowing, and write the overall reaction. Calculate the E cell, meaning the voltage. Write the line notation, or use the line notation in order to draw the picture. Identify the location of the oxidation and reduction. Which side is oxidation happening? Which side is reduction happening? Describe the direction of flow of the positive and negative charges either in the salt bridge or through the porous membrane in order to maintain neutrality. So here's an example. If you're given, I think this is actually number 6 from the worksheet, if you're given this line notation, you should be able to draw a generic galvanic cell. So here are my 2 cells, the one beaker on the left, the one beaker on the right, and they are connected with a salt bridge. The salt bridge has some type of negative and positive ions in there. They don't have to be the same that's in the solution. For example, they might be Na and Cl negative. So that's a salt, that's a type of salt, and you've got salt in this bridge here so that they can flow either direction into either side of the galvanic cell. So in our example, you are told the left side of this is your anode. This is the anode. I'm always going to draw the anode on this side. The metal electrode here is aluminum, and the ions in the solution are Al3+. We don't care what the other part of the compound is, the aluminum compound. It could be, aluminum phosphate, for example. We don't really care. We're just interested in the aluminum ions. And then on the other side, you've got your lead electrode, and you have lead ions in that solution. And again, we don't care what the other ion is to make up the lead compound. It could have been lead sulfate, for example. So this side is the cathode. On the right, you have the half reactions that are occurring here. By the way, if you are given line notation, you're always going to put the left on the left and the right on the right. If you're not given line notation, you've got to figure out which one is being oxidized and which is being reduced. Okay? How do you do that? You do that by looking at the table that I will always give you, and that table is going to show you the reduction potentials. So if I look at aluminum, here it is down here, okay? There's aluminum. It has a value of negative 1.66, and compare that to lead. Here it is. That is negative 0.13. The larger value is always the one that is going to be oxidized. The smaller value is the one that is going to be reduced. So by looking at the table, you will know which one is oxidizing, which one is reduced. So I know now that the lead is going... Sorry, my fault, my fault, my fault, my fault. Back up. I apologize. Let's change that. It's the larger value that is reduced. This is a standard reduction potential chart. Sorry about that. Okay? So the larger number is going to be reduced. It wins the pull on the electrons. So this lead here is going to be reduced. It would be your cathode. We would put that on the right side of our galvanic cell. It would be on the right side of your line notation. The aluminum then is not going to be reduced. It's going to lose the battle, and therefore it's not going to be reduced. It is going to be oxidized, and it's going to lose electrons, and you'll put that on the anode side, which is traditionally on the left. Okay? All right. So let's go back to our drawing here. Oops, sorry. We have our anode and our cathode. This is where oxidation is occurring. This is where reduction is occurring. Electrons are being lost by the aluminum and flowing to the other side. So you need to know which direction the electrons are flowing. Here they are being gained. All right. The electrons are being lost by aluminum metal, and the aluminum metal atoms are turning into ions. Coming more and more aluminum atoms are coming into the solution as aluminum ions. And the lead ions over here are going to be picking up the electrons that are flowing down here, down the lead electrode, and are going to be turning into lead atoms, neutral atoms. As a result, you're going to have more and more positive ions being built up on this side and less of the positive ions over on this side. So to compensate, to keep the neutrality in both of the solutions, you're going to have negative ions flow this way, and you're going to have positive ions flow this way from out of the salt bridge or through the porous membrane. Okay, so you have to know what's going on there. How do we calculate the E cell here? Well, I think I gave you the values before. I'm trying to remember. I think it was 0.13 and negative 0.66. So the larger value is the reduction side. The smaller value is the oxidation side. To find E cell for this galvanic cell, you always just take the larger number minus the smaller number. Exactly the way they're given to you on the table. Okay? So larger number minus the smaller number, that calculation gives you the voltage of this cell. It's basically telling you what is the push or the pull behind, the force behind those electrons. How strong is that push or pull on those electrons to push it from one side to the other side? Okay? Now you were given the line notation here, but maybe I'm giving you the half reactions. Maybe you're only given the half reactions, which are, by the way, the half reactions are, you can get them straight from the line notation, or you can figure them out from what's happening on either side. On the oxidation side, you're going to have aluminum solid turning into aluminum ion by losing 3 electrons. And then over here, you're going to have lead ions picking up 2 electrons and turning into lead solid. I just know because of the change in the charges there. So this is, again, this is your oxidation, this is your reduction. You can figure that out from the half reaction, or you can figure that out from the larger value is always oxidized. The larger value is always reduced. The smaller value is always oxidized. If I was to try to combine these and write the overall redox reaction, I'd have to make sure that elements are balanced, which they all are, and I have to make sure that charges are balanced, which they are in the half reactions, and then I have to make sure I conserve electrons. I have 3 lost, 2 gained. Can't happen. So I have to take all of this times 2 and all of this times 3. Now I have 6 lost, 6 gained. And I don't need electrons in my final equation. Now I can bring them together. 2Al plus 3Pb. 2 plus is going to produce yield 2Al, 3 plus, and 3Pb. That would be your final redox reaction for this particular galvanic cell. Okay? All right, I'm going to mention one last thing here. As I mentioned, I will give you the standard reduction potential table. So you'll have this table available to you. It'll show you the values, or it might just be given right in the problem for you, okay? But those are all the standard reduction potential values that you probably will need. And then this is the rules for assigning oxidation numbers. Those will be provided for you. And then, in addition, I just want to mention one more thing. You might see a table like this in the test, but it might be missing these arrows. So if you do come across a problem that has this table in here and the arrows are missing, I will have it on the formula sheet for you that is provided. Okay. All this is showing is the relative strength of oxidizing or reducing. So if it says a reducing agent, what that means is it's oxidized. And the ones at the top of this list are the strongest reducing agents, or they are the most likely to be oxidized. Metals, look at all these metals here. Metals love to lose electrons. Okay? They love to lose electrons. That means if they lose electrons, they're going to turn into ions, but then that means their ions are going to hate trying to regain. They're not going to want those electrons back. So you'll notice over here on the right side of this table, these are oxidizing agents, meaning they like to be reduced. They like to gain electrons, but notice the arrow goes the opposite direction. These are the weakest. These are the weakest ions that will be reduced. They do not want electrons back. They are metals that want to give up electrons. They want to be oxidized. So the list here is showing you that if a metal likes to be oxidized, then its ion is not going to want to be reduced. If a metal likes to lose electrons, then the corresponding ion that it produces is not going to want those ions, those electrons back. Okay? So that's what that is showing. You'll also notice here that at the bottom of this list are a lot of non-metals. Non-metals like to gain electrons. So you'll notice here at the bottom of this list, these are the strongest elements that like to be reduced. So elements that like to be reduced are those here, these nonmetals like fluorine, chlorine. These are the strong reducers down here. That means the ions they produce are going to be weak oxidizers. They don't want to lose electrons. They want to gain them. Okay? Another way to think of it is what's called an activity series. Again, this is just listing how active certain metals are, or listing how active certain nonmetals are. So you'll notice here the ones that are at the top of the list are the most active here for metals. These are all metals. These are all nonmetals over here. So what this is simply saying is if you see a metal at the top of this list, it is going to be more active than anything below it. Okay, it's going to take over. It's going to be more active than any metal below it. Likewise, if you see a nonmetal, it's going to be more active than any nonmetal below it on this side of the list. And then it also gives you descriptions about how some of those in this particular group, for example, how they react. These most reactive ones, they react with cold water and they replace hydrogen, or they react with oxygen. Notice though, as you move down the list here, they're a little less reactive. These react with water, but it's got to be really hot water. And these here don't react with water. And these won't react with water, but they'll react maybe with oxygen. So you just look at the table. I give this to you. Just look at the table if it's asking you to compare different metals or compare different nonmetals. So for example, this lithium here, all right, if you had lithium and you put that into, it says water, okay, that is going to react. What basically is going to happen is this lithium is going to kick that hydrogen out, and it's going to create like a lithium oxide and hydrogen gas. So you can see bubbles. So anything that is more reactive is going to kick something out. Or if you see like, let's take sodium and HCl. You put sodium in HCl. Sodium is going to kick out the hydrogen. How do I know that? Hydrogen and sodium here is above hydrogen on this list. And then it'll produce H2 gas and NaCl. Okay? Likewise here, fluorine is more reactive than any of these other nonmetals below it. So it'll kick it out of any reactions that you might see. Okay? So I hope this is really helpful. If you've got questions while you're studying, I'm not going to be too available, but you can certainly shoot me an email, and hopefully I'll see it while I'm traveling and be able to get right back to you. So keep working hard. Look at this video, review it, go back over, look at some of the worksheets that I gave you, try those, and hopefully this will be very helpful. Also, you can go to Schoology and do the practice test for Chapter 19 and Chapter 20, and those should be very helpful. All right, great job.